Welcome to the First Mold Insights, where we talk about injection molding, rapid tooling, product development, and real-world manufacturing insights. Today's topic is key design tips for mold runners and subrunners. Alex, we've talked before about sprues as the start of the feeding system, but after the molten plastic leaves that sprue, it hits the runner and subrunner system. What exactly are these, and why are they so critical, even though some designers might overlook them?
Well, Mia, you hit on it right there. A lot of designers, especially newer ones, tend to see runners as just a fixed part of the mold, like it's just a channel. But that's a mistake. The runner is actually the passage between your sprue and the gate. It's the transitional section. Its job is to smoothly redirect that melt. And crucially, in multi-cavity molds, it distributes the plastic to each cavity without a well-designed runner. You're looking at all kinds of issues.
So it's not just a pipe, it's a distributor. And you mentioned multi-cavity molds. Wait, that means single-cavity molds usually don't have runners?
Right, exactly. In single cavity molds, you often don't include a separate runner system. The sprue can feed directly into the gate, depending on the cavity layout. But as soon as you're talking about multiple parts in one shot, or even a complex single part that needs multiple gates, you're definitely dealing with runners.
Got it. So let's talk about the design of these channels. What are the common shapes for a runner's cross-section, and what drives the choice between them?
Okay, so cross-sectional shape is a big one. You've got a few main types, and each has its place. First, there's the rectangular cross-section. That's pretty common because it's easy to manufacture. Tooling design is straightforward, and it gives you fairly uniform flow distribution. You can adjust the dimensions based on your specific molding needs. Then you have trapezoidal runners. These are good for promoting better flow and reducing pressure drop. You typically connect the wider end to the sprue and the narrower end to the gate. That shape really helps guide the melt. Circular cross-sections are also an option. They offer excellent flow characteristics, especially for complex geometries or when you need a really balanced flow across multiple gates. You've got to size that diameter carefully, though, to optimize flow and minimize pressure loss. A variation is the semicircular runner, which is half a circle. This also promotes smooth flow and minimizes pressure drop, often used when balanced flow is key again. Sizing is important. And finally, there's the U-shaped cross-section. This one has a curved bottom and two vertical walls. It's great for efficient material flow and makes it easier to separate the runner system from the molded part, particularly if your gating is located at the bottom of the part.
Huh, interesting. So it's not just about getting the plastic from point A to B. It's about how it gets there and how easy it is to process later. When you're picking a shape, what factors are you balancing? Material properties, part design, what else?
You've got it. Majorum properties are huge. Some plastics flow better in certain profiles. Part design, obviously, because that dictates where your gates can be. Then there's the overall mold layout and your production requirements, like cycle time or how critical pressure drop is. Each shape has its own pros and cons, and you pick based on the specific needs of that particular molding process. There's no one size fits all answer.
Right, that makes sense. Moving from shape to size, what about the actual dimensions of the runners? Does a bigger runner always mean easier filling?
Oh, absolutely not. That's a common misconception. People often think, make it bigger and the plastic will just flow better. But it's not that simple. The size heather, it's the diameter for a circular runner or the dimensions of a rectangular one depends on a lot of things. The product design, the mold construction, and the specific requirements of the injection molding process. While product size and wall thickness certainly play a role, you can't just say larger cross-sections are always more effective metabolite flow behavior. The part's geometry, where you've placed your gates, and all your process parameters those determine the optimal runner design. You're trying to find a sweet spot.
So it's a balance, and you've mentioned material properties before. Are there general guidelines for runner diameters based on the plastic you're using?
Yeah, there are. Or instance, if you're working with a BS or SAN, you're often looking at a runner diameter between 4.8 and 9.5 millimeters. For POM, it might be 3.0 to 10 millimeters. Acrylic can go from 1.6 to 10 millimeters. PA66, also 1.6 to 10 PPO, 6.4 to 10, PPS 6.4 to 13, and so on. These aren't hard rules, of course, but they give you a starting point. It really highlights how much the material itself influences the runner design beyond just the part geometry.
That's really specific and helpful. Let's talk about the layout within the molds. You've got multi-cavity molds, and the runner system has to distribute melt to all of them. What are the different ways to arrange these runners?
Okay, so you're generally looking at two main types of runner arrangements, balanced and unbalanced. In a balanced runner system, the length, shape, and cross-sectional dimensions from the sprue to each cavity are designed to be exactly equal. This is the gold standard for achieving thermal balance and plastic flow balance in every cavity. The goal is consistent part quality across all your molded products. Each cavity fills at the same time under the same pressure. An unbalanced runner system, on the other hand, means the plastic enters each cavity at different times or under different conditions. This can lead to variations in the filling process and potentially different parts. You might see slight differences in dimensions or even warpage between cavities. Now, you might wonder why anyone would choose an unbalanced system, right?
Yeah, that was my next question. If balanced is the gold standard, what's the advantage of going unbalanced?
Good question. Unbalanced systems can offer advantages in certain situations. They allow for more compact cavity arrangements, which can reduce the overall size of your mold template. That can mean a smaller mold, potentially fitting into a smaller machine, or just saving on material costs for the mold itself. It can also lead to a shorter overall runner length, which saves a little plastic per shot. So, it's a trade-off. You're sacrificing some consistency for compactness or material savings. But regardless of whether it's balanced or unbalanced, one critical principle applies. You must ensure your cavities are symmetrical with the center of the mold base. Why? Because that ensures the projected center of your cavities and runners aligns with the clamping force of the injection machine. If it's off-center, you get tilting moments during injection, which can lead to flash or uneven filling.
Right, so even if the flow isn't perfectly balanced, the mold itself needs to be. That makes a lot of sense for machine stability. So, when you're designing these runners, what are the core principles you're always trying to achieve?
There are a few key principles we always follow. First, you want the molten plastic to enter the cavity swiftly, taking the shortest distance possible, and with minimal heat and pressure loss every bend. Every long path costs you energy and heat. Second, especially for multi-gated parts or multi-cavity molds, you want the melt to feed into the cavity simultaneously from various gates under identical temperature and pressure conditions. This ties back to that balanced flow idea. Third, while larger cross-sectional areas do make molding easier and ensure adequate packing pressure, you also have to consider material saving. You want to aim for smaller cross-sectional areas to minimize plastic consumption. That also helps reduce cooling time, which is a big deal for cycle time. So, to conserve material and aid cooling, you strive for a minimal surface area to volume ratio in your runners. You want to get the plastic through efficiently, without wasting it or taking too long to cool. And then surface roughness. You might think, make it super smooth, but actually the surface roughness of runners shouldn't be too low. If it's too smooth, you can drag cold material into the cavity, which causes issues. Typically, an RAV value of 1.6 micrometers is sufficient. It's a sweet spot. Finally, runners and gates are usually connected with slopes and arcs. This isn't just aesthetic. It promotes the flow and filling of molten plastic, reducing flow resistance. Sharp corners are flow killers.
So, you're balancing efficiency, material usage, cooling time, and even a bit of intentional roughness. That's a lot to consider for what looks like a simple channel. Now, about subrunners. Are they always necessary, or when do they come into play?
Subrunners aren't always necessary, no. They're typically used when you need to divide the flow of molten plastic into different directions within the mold cavity itself. Think of it like a smaller secondary manifold. They can really help facilitate the filling of complex parts or multi-cavity molds by directing the flow to very specific areas or components of the part. If you have a really intricate part or a mold with cavities that are far apart or oriented differently, a subrunner can be crucial for getting the melt where it needs to go precisely. But in many cases, a simple runner design without a subrunner is perfectly sufficient to achieve good mold filling and part quality. It really just depends on the specific requirements of the part design and the injection molding process you're using.
It sounds like a lot of these decisions come down to careful analysis of the part, the material, and the production goals. It's all about thoughtful design, not just picking defaults.
Exactly. It's about understanding the physics of the melt, the demands of the part, and the economics of production. Don't just copy what you've seen before. Understand why a particular runner design works for a given application. That's how you deliver top quality molds.
Thanks for tuning in. For more manufacturing resources or custom part production services, visit firstmold.com. We'll see you next time.